Buongiorno, bonjour, guten Morgen, ciao buisan, dzień dobry, buenos dias, and good morning. Welcome to episode number 26 of the ZOOMTOWN experiment. Today's episode, we're going to focus on just getting the Zoomie to move. This won't be the refined motion control that ultimately we'll have, but we do need to start somewhere. And because there's a lot to discuss on it, the whole velocity control and position control is split up in several segments. So we'll be seeing those in the coming weeks. Just as a heads up, if you're watching this as a new video, just published, I may be falling behind on schedule a little bit over the course of the next month or so. Hopefully it won't be anything more than a missed week or two in the normal schedule. So back to today's episode, we're going to start by taking a look at the code, and then we're going to reflect back over to the schematic so we can kind of tie the two together. Then we're going to look at the hardware, and then we're going to see if we can't make this little guy go rolling across my desktop and, not catch on fire or something. So let's take a look at the code. The thing I want to focus on right away would be our hardware. These are the pins related to the motion control. We're going to have a PWM output that's going to be on pin 21 for the left motor and pin 18 for the right motor. And that would be, so to speak, driver's seat of the Zoomie. That's how I keep straight left versus right. It's from the driver's seat of the Zoomie, so to speak, just as it would be in a car. We're going to set the frequency for that PWM signal using these two commands. And then for directional control, it requires two inputs to set which direction you want each motor to be at. Kind of wasteful, but I think I understand why they went with two pins as opposed to just one pin saying on, 1 for forward, and 0 for reverse. Nonetheless, it just does require a total of 2 pins for each motor. So 19 and 20 for the left motor, and 16 and 17 for the right motor. Now let's take a look at that in the schematic form. Let's start with what we're aware of. We got 2 motors, a left and a right motor, and they're N20 6-volt 100 RPM gear motors. Here's my 6-volt supply coming in to our TB6612FNG chip, breakout board, however you want to phrase it. And those would come in at 6 volt would be VM for motor voltage, and then 0 volt into ground. Off to the left, here's our 3.3 volts coming in. That will feed into our standby, so that's always pulled high, meaning it's active and not in standby state. And then we're going to bring it in on VCC and, of course, in on ground. And then this is another ground connection back. It's just from a different location on the circuit boards that I'm using. Going out to the motors, we've got B01, B02 going to the motor, and right motor, and A01, A02 going out to the left motor. They're straight up DC motors. It's not like a stepper motor where you would have 4, 6, or 8 wires. Over here, we've got our PWM going in at GP18, and for PWM-A, GP21, we're using 16 and 17 to control the B motor for our directional signals, and 19 and 20 are directional controls for our left motor. Not a lot of magic in this. It's all just straight up wiring, and I'm using DuPont connectors where I can. These motors are very low current, very low voltage, so I can easily get enough current through a DuPont motor or through a DuPont connector to make the wiring of this as simplistic as possible. Now let's take a look at that on the Zoomie itself. You can't really see too much, so I'm going to grab a little pointer here. On the lowest deck is the motor control deck. You'll see inside, boy, it's next to impossible, but this group of wires here are most of the control wires going to the motor driver chip. Coming out this side, these are the wires going to the power supply and off to each of the motors, which is also very hard to see, but you can kind of see right here is the motor. This would be the left motor, the right motor. There's an insulator between the two because their terminals or their contacts are darn near touching. The only thing separating them is this insulator, but that's where the two motor wires go for each motor. If you don't remember, this is what the motor driver chip looks like. Of course, we put headers on it so that we can connect it to our motors. This is the whole motor, gearbox, and then output shaft. These are the two input wires, positive, negative, and they do mark the motor for which one should be positive and negative, but as we all know with DC motors, in all likelihood, it really doesn't much matter. As a reminder, for this episode, we're only planning the most basic control. I'll have the Zoomie move forward and reverse. That will require us to be able to set the direction pins for each of the motors. And we'll need to set the velocity, the duty cycle for the PWM. That will allow us to control the speed. I'm not too concerned about variable speed at this point, but we know that in the practical application, I'm going to need variable speed for each motor because in order for this to turn, one wheel has to spin faster than the other. That's how it turns. We will also need to have variable speed control to do simple steering, either driven by encoder feedback or through the optical sensors that are on the front of the Zoomie that do the line following. So variable speed is going to be very important, and that will be a big part of a discussion, most likely in our next episode. I can't focus on acceleration or deceleration. In fact, we don't even know if we need it yet. Oftentimes in robotics like this, people just simply turn on the motor and let it move, turn off the motor to stop it. And that works perfectly fine for most applications. Our application is a lot more unique than just moving from one location to another rapidly, and we don't care how accurately it is. We need to have much more control over position. And you're going to need more control over the motors. For example, if the tires slip while accelerating, we lost positional tracking. If the car skids a little bit while braking, we've lost positional feedback. The Zoomie could also get twisted, either turn left a little bit or turn right a little bit. Again, that would create problems for us. So we'll see the importance of acceleration and deceleration in a future episode. Let's dig into the code right now. Down in my velocity control area of the program, we're going to have two functions that each will set a wheel's direction of rotation. And one will, of course, be for the left wheel, one will be for the right wheel. Other than that, they're identical functions. We're going to be storing that direction into a global variable. And this function only receives the direction. The assignment of that to the global variable happens in this function. Now, that direction would be in the form of a three-letter command, FWD for forward, REV for reverse. So that's how I tell it which way I want the motor to go. And then we just set the output pins that go to the motor driver to get the direction we want. So in the case of our left motor, left wheel, if the direction is forward, we would set the left direction input pin number 1 and pin number 2 as 0 and 1. And then we would reverse that in order to get our reverse motion. So it's just a matter of which one is on, either 1 or 2, related to this, as to how we make the motor go forward and reverse. And these functions are identical with the exception one is operating on right wheel, one is operating on left wheel. Now, I'm going to skip over this adjust run velocity, and we'll just go to set velocity to begin with. Now, some of you in the rest of the world other than the United States, you'll be upset by this, but I am working in inch units for almost everything in this whole process. In my definition for speed is in inches per second. For me, it just worked a little easier with the math in my head and trying to keep all of this straight. So I went with that. Inches per minute would be too coarse. I needed a finer control. That's why I went down to literally distance per second, as opposed to kilometers per hour, kilometers per minute, or miles per hour, miles per minute. Way too coarse. We would never get the precision and resolution that we need to do very fine control of these velocities. So in coming to the set velocity function will be the left run velocity and right run velocity in inches per second units. Now, you'll see that in here we're going to convert those inches per seconds to duty cycles, and that is a function of a little bit of math. We're going to, for example, our L_DC, left duty cycle, is the integer. Remember, well, you probably haven't been told this yet, but the motor driver wants, or the PICOW or PICO wants duty cycles specified in integers, not floating point. So we want to make sure we convert that into an integer. But we're going to take the left run velocity in inches per second divided by the max velocity, and we'll multiply that times 655, 535, which is 100% duty cycle. That will give us the duty cycle and store it into L_DC. Now that max V, you might be wondering, well, what is that max V? Let's look at that in our list of global variables, which should be right above. Max V is 9 inches per second. Now, that's not an arbitrary number. That's coming from a little bit of practical testing, but if you take our 6-volt motor, run it at max speed, it should generate 100 RPM minutes, and if we take that times the circumference of the wheel and divide it by 60, we're going to be in that approximate area there. I believe it worked out a little bit less than 9 inches per second. But in practical testing, I think I was able to achieve 9.5 inches per second at full 100% duty cycle and at the voltages coming out of my power supply, which is 6 volts. So that's our max velocity in inches per second. There is also a minimum velocity of 0.9 inches per second. If I specify anything lower than that, the wheel will not turn. It just doesn't have enough power driving the motor to actually make it move. And that's actually a little bit of safety factor in there as well. And we'll try to demonstrate that a little further along in this video. But those are two very important variables that give us a working range for our velocity in inches per second. So we're all the way down here. This function again, we take our desired inches per second divided by the maximum inches per second to get a ratio, or a factor if you will, and we multiply that to times the maximum amount of duty cycle, which is 655/35. We then, after setting the velocity, we will call adjust run velocity with our left and right duty cycle values, and that's this function, which simply sets the PWM signal for the motor driver for both left motor and right motor. It's truly quite that simple. I don't know if I can explain it any simpler than that. So from here, this is what we're going to use right now for our velocity control. Eventually, there's going to be a lot more complex computations added to this. But for us to just get the Zoomie to move, this will get us going, and I could even set directions. So with that, we will work on setting up a testing method for this because we don't have positional feedback yet. The encoders are there, but we haven't coded that yet. So what I want to do to test this, I'm just going to let the motor run for, say, 6 seconds at a velocity, stop it, and then go in reverse for 6 seconds at the same velocity and stop it. And then we'll see what the behavior is based on that. Okay, I've thrown a little bit of code together within our main loop, which, as you remember, it's a deterministic loop. It runs every 5 milliseconds. So from that, it's kind of pretty easy to derive how many clock cycles or how many loop cycles we need to get 5 seconds of travel and, say, 1 second of dwell in between forward and reverse. So here is where this will be in our code. This is the start of the main loop, and this is my little test code. We're going to be monitoring a loop counter, which is incremented here every time the loop executes. So we're just going to sit here and wait for 1 second before starting. And then after 1 second is passed, which would be 200 times through the loop, we'll set our wheel directions, and then we'll set our velocity at 4 inches per second, and then that will cause the Zoomie to start moving. And I'll print out go forward so I can kind of keep track of what I'm doing. After moving for 5 seconds, which would be 1,000 on our counter, got to subtract our 200 there, we'll set the velocity back to 0 and stop. Then, after another second, we'll start moving, this time in reverse. So we'll set the wheel directions in reverse, and we'll set the velocity again at 4 inches per second. We'll go reverse, and then after 5 seconds, we'll stop by setting our velocity back to 0, and we'll break out of the loop to terminate the program. Now let's just watch it run, and then we'll repeat this a couple times, and I'll explain to you what's going on here. So we'll hit start now. It should be coming in from the right side of the camera. Notice it kind of wanders, right? And it kind of jerks and when it goes into reverse there. And it ends up crooked. So let's watch that again. And you're going to get a real good idea why dead reckoning on robots isn't the best practice. So now we're going to go forward again. They're both commanded to go at exactly the same speed, so it should go perfectly straight. But you see it wandering, right? Now, there's a couple things influencing that. One, these are 3D printed wheels, so they're not absolutely perfectly round or perfectly the same size. That's going to be very critical for the determination of actual velocity. So that's causing some of that wandering you see going back and forth. The wheel, if it's not perfectly round, it'll go slow for a while, go faster, slower, faster, depending on how far the bump is from the center of the axle. Remember, it's all about circumference here relative to the center line of the axle. So that gives us a little bit of wandering, but then when you see it going off at an angle, that isn't wandering because of the wheel size. That is one motor's going slower or faster than the other. So we'll get there, and it always seems to be in the reverse when it does. There it goes. Now it's turning. Oh boy, we got lost there, didn't we? That should be very clear as to the importance of what we have to do with wheel encoders so we can make sure both wheels are traveling at the same velocity. We can do that by measuring the distance traveled between a certain period of time and calculate its velocity. Also, line following helps guide the robot if we're using the two photoreflective sensors at the front of the robot. Those allow for a very fast feedback loop as to whether the Zoomie is going straight or if it's wandering off. And it doesn't require a lot of mathematics to deal with it. So it's a very efficient way of moving, not necessarily just in a straight line, but you can also go around curves and everything else. In our case, we're going to just make that a little more complicated just because. Now let's go ahead and bump this velocity up. We're going to go up to, say, 8 inches per second, which would double it. And because it'll go twice as far, I need to adjust my durations. Because if it's going twice as fast and I go the same amount of time, it's going to fall off the end of my workbench on the left-hand side. We don't really want that. So instead of going 1,000 more than this, I'm going to go 500 more. So that would be 700. And we'll still wait for a second here. So that would be 900. And then we'll go 500 on top of that. So that would be 1,400. And from there, we should go twice as fast, but approximately the same distance if everybody plays nicely here. So let's see what this brings us. Whoa, whoa, we got a couple wheelies there. This is where acceleration and deceleration are going to be very important. Now, you're looking at it from an overhead view. I'm going to get a camera set up so we can get a side view of what's going on there. And that'll give you a little better perspective as to the trouble not having acceleration and deceleration is. So give me a few minutes to get that all set up, and we'll share in the fun with that. Okay, now let's take a look at what a forward wheelie or a stopping wheelie looks like, and then a reversing wheelie. Give you one more shot at that. You'll get an idea of how important acceleration and deceleration are. And from the overhead view, you see how far we're getting out of alignment. So acceleration and deceleration have to be implemented in this situation. Now again, if we've got just a simple little silly robot that we want it to go forward or reverse and wander around the floor, all that's fine and dandy. But in truth, I need to maintain somewhat positional accuracy within, say, a 1/16 of an inch over this entire layout, which is 8 feet by 4 feet, or I think it's a meter and a half by 3 meters, I think is the quick conversion on that. So in reality, if you want to get into the metric perspective, we would need to be in position within a couple of millimeters over the entire travels across that 1.5 meter by 3 meter layout. So the complexity now goes up dramatically. And with that, we're going to need positional feedback. In order to accelerate, it's pretty simple. You start out at some minimal velocity. And we'll go ahead and demonstrate that here, where if we set it too low, the Zoomie simply won't move. So let's go ahead. And what we'll do, we'll set our velocity at 0.5. Okay, that's really slow. 0.5 inches per second. I'm not sure if that's going to be slow enough to really make it mess up, but it's worth a shot. Okay, so let's see what that does. Okay, it's not even moving. So that'll give you an idea if we set the velocity too low. Let's bump it up to, say, 1.5. And I'm quite sure that is the minimum, above the minimum velocity. As I remember, it was 0.9. So let's see what this does. That is 1.5 inches per second. Not going very far fast. And you just saw it lose position as well. So we do need to make sure we're giving it enough velocity so that it moves reliably. We'll give that one more test here. I may actually have to bump up my minimum velocity that I developed earlier. Okay, so it's just functional there. We're wandering, but again, that can be dealt with in a different way. So as you can see, this is quite a complex concept to be able to move very accurately. We can see why dead reckoning won't work. Dead reckoning is the process of point it in a direction, tell it to move for X number of seconds, and expect it to actually get to that exact location in two dimensions. We just saw here it didn't work, and that is very common. So to deal with that, we're going to add in a number of functions that will help allow the Zoomie to travel in a straight line, either guided by encoders or by markings on the road surface. We also need to incorporate acceleration and deceleration, because if the Zoomie's doing these wheelies starting and stopping, it's very likely it's going to change direction, just as we saw demonstrated there. So I need to incorporate acceleration and deceleration into the velocity control. On top of that, the system is also going to have an override control, so that over at the control system for ZOOMTOWN, I can override the speed of all the Zoomies simultaneously, anywhere from 60 to 100%. Further complicating it, if the Zoomie encounters something in its path as it's moving along, it will have to decelerate to a stop, wait until the blockage is removed, and then accelerate back up, all unattended and automatically. Hopefully you start to see what's all going on here as I build these pieces together, and why I really can't do this all in one video. It's just, I can't talk that, well, I probably can talk that long, but you guys would fall asleep long before we got to the end of it. So where we need to go next, I need some feedback information in our control loop. And that feedback information I want next will be our encoders. The encoders give me very specific data about the rotational speed and how far it rotated over a given period of time for each wheel. And that will give us some feedback at which we can start working with acceleration and deceleration, and then as things evolve into more refined control of the Zoomie's movements. So we'll wrap up this video right now. I think I got a little long, but we're in really good shape now with this baseline to move forward into all the more complex functions. I look forward to seeing you in about a week, and at that point we'll be talking about encoders. Thanks again for watching. We'll see you then.